Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be doing an example walkthrough of a collision between a puck and a stick. This is a continuation of our discussion of rotational dynamics in general and of collisions between extended bodies and conservation of angular momentum in particular. There's a number of examples that we could be doing in today's video. I'm going to be doing just this simple example in which I have a puck or a little disc that's going to collide with a stick which is on a frictionless surface, and just for the fun of it, the stick is free to move, but it's initially at rest, so v equals 0 initially for this stick. The puck has some initial velocity. The basic parameters are kind of in this diagram. There's like a mass for the stick, there's a mass for the puck or for the disc or whatever you want to call it. Other than that, we have an initial velocity, we have a length, we have a center of mass location. We're maybe assuming that the puck is relatively small compared to the disc, so any moment of inertia contributions are that this is sort of like point-like. So we're making this simplification. And from here, the only other piece of information we would maybe need is like, where does this impact? And so I've labeled that as like mu times L. And then one condition about the collision, meaning, is this an elastic collision? Is it a perfectly inelastic collision? Is it a collision in which we happen to know one or another of the end values, that kind of thing? So for today's video, we'll just pick one of these for the example. Now, the basic walkthrough of what we have to do in a problem like this is, first we've got to figure out, given the parameters, what the moment of inertia is of each object about some common center axis of rotation. And we also would need to know something about the, basically like where is this located relative to the ends, and therefore where is the center of mass for the whole system. Generally speaking, we would take the center of mass of the whole system as our axis of rotation unless we have some reason to do otherwise, essentially. For our example, we'll take a small puck colliding with a stick. It's basically like a rod-shaped stick, and the two will be stuck together after the collision. We're given the initial speed of the puck, we're given the stick's mass and length, we're given the location that the puck impacts the end of the stick, and what we're trying to do is figure out what the final speed and rotation rate and maybe energy loss all are. So if I was going to draw this situation from initial, I basically have something that looks like this, wherein I've got a little puck coming towards the end of the stick. I'm told that this distance right here basically represents 20 centimeters, so this is 20 centimeters. I know that the whole thing is 2 meters long. I know that the center of mass of this symmetric stick should be 1 meter. And I have to find where the center of mass of the system is. So center of mass of system should be somewhere over here. So I'm going to call this system center. And that is immediately after impact. So at impact. And essentially we care only about the axial center of mass for this system here. So right after the impact has occurred, or maybe I should say like the moment of impact, you have a situation that basically looks like this. And so my little puck is right here. I have somewhere a center of mass of the whole system about which the system can rotate. And in addition, the system together will be moving like this. So I have like a final speed, I have a final omega, and I have an initial speed. The initial speed is given right here, v initial, and these two things, the final speed, v final, and the rotational speed, omega final, are two of the things that we're looking for. So our first step is we need to figure out where the axis of rotation for this system will be. And since everything is free to move, this axis of rotation should be the system's center of mass. So to find the location of the center of mass, what you should be doing, and I should pause here for a moment and say, yeah, the center of mass I've drawn in my diagram as if it's like right here in the stick. It's probably like slightly shifted downward because of the disc, and slightly shifted over from the center of mass of the stick, again because of the disc. But the main thing that we need to know is like, where is the x value of this dashed line that I've drawn? We don't care really as much if this is up or down on this line, as long as it's a small amount. We really care mostly where the line is. Otherwise, the calculation becomes overly complicated. So we are doing a little bit of approximation here. This center would shift very slightly, and some of that depends on how thick this stick is. We're taking it to be a really thin stick. Okay, so that means that the position is close to, but not exactly in the center of the stick axial, but we need to know where is it along the up-down direction, or excuse me, we need to know where this dashed line of like up-down directions is relative to, say, the end of the stick. So in some sense we could call this x center of mass to be from one end of the stick to here. We could also use the center of mass of the stick as our location, or the end of the stick, or something like that. If I use this as my center of mass location, remember that to do that you add up the center of mass, you add up the mass times the distance from your common point, and then you divide by the total mass. So that basically means that I'm looking at L over 2 times mass of stick plus essentially L minus 20 centimeters times mass of the puck, or of the disc. I think we've been labeling it MP, so I better keep that consistent. And then we're dividing by mass of stick and mass of puck together. So this ends up being 2 meters over 2 times 4 kilograms plus essentially 2 meters minus 0.2 meters times 200 grams, which is 0.2 kilograms, all divided by 4 kilograms plus 0.2 kilograms. So my center of mass location is 1.03809523 meters. We will maybe take that to this digit here, and so my center of mass location from the end of the stick is about 1.04 meters from the end of the stick. And actually even that is doing some interpretation here, that yeah, when we say the impact is 20 centimeters from the end, we also mean that the center of the puck is, and that's not a very unreasonable interpretation. It's quite reasonable for that particular interpretation. So our center of mass is 4 centimeters off from the actual center of the stick. Okay, so that is our first step. Second step, now we can figure out how momenta and angular momenta will be conserved. Conservation of linear momentum says that mass of the puck times the initial velocity is equal to mass of the puck plus mass of the stick times the final velocity. This is basically coming from the fact that we initially had a stationary stick and a moving puck, and we finally have both of them moving together. So this is just simple linear momentum conservation. This basically means that my final velocity should be this ratio of puck divided by puck plus stick masses times the initial velocity of the puck, which was 25 meters per second in some direction. We're looking for just the speed, so we can drop the directions. We end up with 0.2 kilograms divided by 4 kilograms plus 0.2 kilograms, all times 25 meters per second. And so that gives us a total of 1.19 meters per second. So let's, without rounding, it's 1.190476619 meters per second. Or put differently, my final speed is approximately 1.2 meters per second for both together. Third step is basically to do this again for angular momentum, but to do that, there's some additional steps. So third step, conserve angular momentum. And conservation of angular momentum requires that the L initial and L final be equal, but that's the same thing as saying that the mass of the puck times the initial velocity of the puck crossed with the radius, the distance at which the puck is impacting our system relative to the axis of rotation. So this would be times essentially L minus 20 centimeters minus X center of mass. So this is like where does this impact occur relative to the center of mass of the system. And that in turn should be equal to the moment of inertia for the stick times omega final plus essentially the moment of inertia for the puck, which again, even though the puck has some thickness, we're going to approximate it as a point-like thing. And so that would basically just be mass of puck times, and we could call like this whole distance r. So it'd just be mass of puck times r squared times omega. Okay. Where this omega is omega final. So if this whole thing, if we're saying r is equal to L minus 20 centimeters minus X center of mass, that is 2 meters minus 0.2 meters minus 1.04. That was what we found up here, 1.04 meters. And so that ends up being 0.76 meters for what it's worth. And so what we have here is that M times VI times R is equal to I stick plus MP R squared omega final. And therefore omega final must be this ratio, essentially of MVR over IS MR squared. Okay, so that gets me my omega final. I still need to figure out I stick. So what is I stick? I stick is basically we have a rod that's being spun about an axis through its center. you end up actually having a somewhat complicated looking formula. Basically what's going on here is that this right here would be the moment of inertia of just a thin rod with an axis through its actual center, and this is the formula that we add to that because the axis of rotation is not through the exact center. With numbers in, that means that the moment of inertia for the stick ends up being 4.0 kilograms times 1.04 meters minus 1.0 meters squared. That was the first term here. Plus 1/12 of, and then the length is of course 2.0 meters squared times the mass 4.0 kilograms. So if we put all of that into a calculator, the first term 0.04 squared is going to be a fairly small number. So when multiplied by 4, this whole term right here is 0.0064 kilogram dot meters squared, roughly. And this term right here, I have basically a little more than 1 1/3, or basically like 1 1/3, I believe. So this is like 1.33 kilogram meters squared. So this is actually pretty small compared to this, almost minuscule, basically negligible, and that's why a lot of textbooks ignore, when working a similar problem to this, they will ignore the fact that you're not spinning about the actual center of mass of the rod itself, because this effect is just not that big. So for a good approximation, maybe you'd stop here. We could maybe say like the eye stick is approximatable as 1.339 something, and so maybe we'd say 1.34 kilogram meters squared. All right, so now we're ready to take that and put it back into our original solution, which is this guy right here, to get our final angular speed. So omega final should look like, again, mass of puck, initial speed of puck, times distance between puck's impact point and the center of our system. So that's 0.76 meters worth. So I've got 200 grams, which is 0.2 kilograms, times 25 meters per second, times 0.76 meters, all divided by 1.34 kilogram meters squared plus, and then this other term, the mr squared term, is mass of the puck specifically. And so again, that's 0.20 kilograms times your 0.76 meters squared. So if we go and add this to the I, then what do we get? We got 0.2 times 0.76 squared, which is 0.577. And so what we end up with on the bottom, this whole bottom term, is 1.45492 kilogram meters squared. Okay, so that is being divided into 25 times 0.2 times 0.76. So that ends up giving us an omega of 2.611827454. So let's call that roughly 2. We'll write the whole thing out. 2.611827454 radians per second. And obviously we only want to retain maybe two significant figures worth of that. So this is 2.6 radians per second for the final speed. Last part of this, fourth part, whatever you want to say, is energy. So we could say energy considerations. Now initially what we have is a moving puck. So K initial is 1/2 mass of puck V initial squared. So this is 1/2 times 0.2 kilograms times 25 meters per second squared. So 0.2 times 25 squared divided by 2 gives us 62.5. So 62.5 joules. Finally, we have a little bit more of a calculation. We have K final is 1/2 m puck plus m stick V final squared, plus also 1/2 I stick plus mass puck R squared times omega final squared. So we have both a translation, this is your translation, and a rotation. So let's take those two in turn, shall we? K final translation is just given by 1/2 of 0.2 kilograms plus 4.0 kilograms times that final speed, which if we go back up here was about 1.2 meters per second, 1.190 whatever. So 1.190 meters per second, and that's got to be squared. All right, so 1.19 squared is 1.41 times half of 4.2 gives us 2.9738 joules. So we'll just call that about 3.0 joules. And our final rotational is 1/2 of I stick, which again was about 1.34 kilogram meters squared, plus mass of puck 0.2 kilograms. We already kind of did this calculation down here. We got 1.45. So let's just put in the 1.45 here again. So 1/2 of 1.45 kilogram meters squared times omega final, which we just found was 2.611 or whatever. So 2.611 radians per second squared. Okay, so 2.611 radians per second squared times 1.45 times 0.5 gives me 4.94. So we have roughly 4.94 joules. Okay, total, when we add all this up together, this one, I guess we could just put in the 2.97 since I've kept so many sig figs there. So plus 2.97 gives me 7.91. So K final is about 7.91 joules. So how much energy was lost? Delta E is K final minus K initial. So that is 7.91 minus 62.5. That means we have a loss, delta E loss, of negative 54.6 joules. So this is 54.6 joules lost in this collision. All right, so this was a pretty long video to work through this whole example. I tried to walk through each step of the process. You can see why it is that this one example gets its own video on the one hand, but also why I didn't include it in the original video. With my trying to keep these under 20 minutes, even under like 15, 16 minutes is usually my target for these. And this video's, you know, well over 20, close to 25, 26 minutes long. So I know it's kind of a longer one that I usually do. Thank you for bearing with me through it. Hopefully you got something out of it for your time. And as always, thanks for watching.